And I want to give you another toolkit in your machine learning toolbox, and that is dimensionality reduction. The power of dimensionality reduction is very important because you cannot visualize a higher dimensional data, but you can visualize a two-dimensional or three-dimensional data. So for to implement your unsupervised learning algorithms, you have to see whether your data is separable or not. Like visualizing the data is important. That's why dimensionality reduction comes in handy during unsupervised learning. It's a very useful thing in unsupervised learning because you can reduce the dimensions without affecting your dataset, your normal structure of the dataset, and you can visualize whether your data is separable or not, because you cannot draw 4 or 5 dimensional or even 13 dimensional graph, but you can visualize a 2 or 3 dimensional graph. So, and on the flip side, high dimension data is extremely complex to process due to inconsistency in features, which increases the computation time and makes data processing very difficult. So there is a thing, using large data set has its own pitfall, that is also known as curse of dimensionality. And because there might be redundant data, inconsistency in features. So, and some features could cause biasness, like you can have large values in case of some feature, and those features will have large weight with them, and that will cause your model to be biased towards certain features. Mm, So, dimensionality reduction is very useful. So, there are certain techniques of dimensionality reduction. There are many techniques like principal component analysis, single variable decomposition. So what principal component analysis does is we'll learn principal component analysis, which is one of the most popular and powerful technique for dimensionality reduction. What it does is it enables you to identify the correlation and patterns in a dataset so that it can be transformed into a dataset of significantly lower dimensions without the loss of any important information. You can also check how much information you lost when you do the principal component analysis, because you're reducing, for example, a 13 dimensional data into 2 dimensions. So when you do that, you will obviously lose some information. Dataset, which is breast cancer dataset, and we'll load this dataset into a variable called cancer data, and after loading it, we'll look at the keys that this bunch type object has. So after looking at the keys, we'll look at the target names it has. Like it's like normal, I'm just exploring the data. So here you can see there are two types of data in this data set. One is malignant and another is benign. So what this says is like benign cells are harmful and those cells can be cancerous, and on the other hand malignant cells can be non-cancerous. So let's look at the shape of the data. So here you can see I've called this cancer.data.shape. On the other hand, you can this both, you might get confused when you look at the syntax. So this, you can call the data either as a variable in the cancer data because you have loaded it, because in the cancer data is a variable, or you can also get it by using the data as the key. So, so these two lines mean the same thing. So if you do not get, for you to not to get confused, I've just showed this. So after doing that, we'll convert it into a data frame by passing the features and the feature names as the columns. So let's see, and I've also used that cancer df dot assign method, and I've showed you what assign method does. So assign method is a way of adding a new column where the column name is target, and in the target I'm passing all the cancer data dot target. So I'm passing all the values in the target list. So here you can see the targets. So suppose 0 means malignant and 1 means benign. So after exploring the data, let's see the performance without dimensionality reduction. As I said you, due to dimensionality reduction, you lose some information. And as a result of losing some information, what will happen is your performance will decrease. So in order to see how much our performance decreases, we will see the performance beforehand, like performance of the performance of any algorithm on this dataset without a dimensionality reduction. So in order to do that, I will use the train test split function. And as I have spoke about this function a lot of times, I'll not go into the details of this function. So after splitting it, we'll take the X train and the Y train, and the X train contains all the features and the Y train contains the corresponding labels, whether the cell is malignant or benign, and we'll use the k-neighbors classifier from sklearn.neighbors, and in k-neighbors classifier we'll use 4 neighbors. So on the basis of 4 neighbors, it will decide which class to label the new sample it sees. So when no dimensions are reduced, let's see what's the performance of this model. So here you can see the performance of the model is really good. We have a training accuracy of 95% and a testing accuracy of 94%. So your model fits the data well, and the testing accuracy on the data points it did not see is good as well. So, and now we want to analyze the performance after some dimensionality reduction. So we will reduce some dimensions, and the preliminary step before you can do the principal component analysis and dimensionality reduction, what you have to do is you have to scale your data, because if you do not scale your data, there might be some biasness when the dimensions are reduced. So scaling the data is a must when you do principal component analysis. And scaling the data on certain datasets depends on the dataset. If your dataset has variables where the variance is quite high and the all the sample points vary a lot, then using a scaler would be a very good advice. Or if you have like a table or a column where there are large values at a point, and where there are large values recorded at certain time, and at another time there are relatively very small values, so in that case using a scaler would increase the performance of your model. So when it depends on your data set when you should use a scaler or not. And what a scaler does is, we have gone through all this in the pre-processing lecture. So what a scaler does is, it basically scales your data and brings it close to the origin, or it fits your data within a range. Like for min max scalar, it fits your data within the given range. So that what scalar does. And some of the scalars are very robust to outliers. For example, we'll be using the standard scalar here. So I'll import the standard scalar class, and with that class I'll create an object of scalar, and using that object I will fit all the data. I will fit all the feature values. I'm scale using scalar.fit transform. I'm fitting all the feature values, and I'm creating a new data frame. I'm creating a new data frame. You do not have to do it. You can just fit your data and then split it into train and test. I'm just creating it to show how the data looks. So after doing that, let's look at our data after transforming it. So here you can see the data is bought within all the values are somewhere within the range of 3 and or 5 and somewhere close to -2 or something like that. So here you can see we had relatively large value for some of the columns. For worst texture we had some large values, but for if you look at this data set, then for where is worst texture, so for worst texture the value are shrinked, so and brought within a range. So that what scalar does, and before you can do principal component analysis, scaling is a must step. So what principal component analysis does is it computes the covariance matrix, then it calculates the eigenvectors and the so eigenvalues and variant vectors and values. What they do is they find out where in the data there is maximum variance, or you can, in other words, you can say maximum information. So the steps in principal component analysis are: first you have to standardize the data, which is scaling the data. Then after scaling the data you have to compute the covariance matrix. Then on the covariance matrix it calculates the eigenvectors, eigenvectors and eigenvalues. And using this eigenvectors and eigenvalues, you can calculate the maximum variance, which actually denotes where in the data you have the maximum information. And after that you can calculate the principal component analysis and principal components, and then you can reduce the dimension of the data. So you do not have to do all these steps, and that's why I said with using scikit-learn with minimal code adjustments you can do a lot of steps together. So all these are done under the hood for you. If you want to go through it, you need to read certain papers and you need to see the tutorials how these classes are built, this principal component analysis PCA class is built. So from sklearn.decomposition I will import PCA, and the number of n components I want is 2. So what I mean by that, here you can see, let me print how many. So let me see how many feature values we have, that is how many columns we have. See here you can see we have 30 features in total. So I'll be reducing this 30 features to only 2 features. So I'm reducing it to only 2 features because I want to visualize the data later on. So in order to visualize the data, I need to reduce it to 2 features, because you can only visualize 2 or 3 dimensional data. You cannot visualize more than that. So I'll be creating a PCA object with this class, and after creating it, what we need to do is we need to do pca.fit transform on the cancer data.data, because we'll be calculating our principal component analysis on the features. On the features we'll be calculating our principal component analysis, because on the features it will calculate the covariance matrix, and on that it will calculate the eigenvectors and eigenvalues. So after that it will calculate the principal component analysis. So in order to do that, I have you can see the principal component analysis here. If I print it after fitting and transforming it, so here you can see it has been reduced to two dimensions. Our 30 dimensional data is reduced to only two dimensions. So this the first row of 30 dimension is only reduced to only two dimension, which I can call as principal component 1 or principal component 2. You can also look at the explained variance. So what explained variant does is it shows you how much information you lost, how much information the first variance contains, and how much information the second variance contains. This column is the second principal component analysis, and this column is the first principal component analysis. So this explain.variance.ratio shows how much information you lost. So if you add these two up, if I add them up, so here you can see we did not lose much information even after reducing the data to only two features. From 30 features, we have reduced it to only two features, but we did not lose much information. So since we did not lose much information, our performance shouldn't drastically decrease. So let's see. Um, Before doing that, what I will do is, so here what I did is I've created another data frame, and this in this data frame what I did is I have firstly I created a new data frame with the principal components that I have saved in this variable principal components, and with that I've created a new data frame where the column names are principal component 1 and principal component 2, and I'm not printing this line, so I'll comment it out. And using pandas.concate, what I'm doing is I'm concatenating two data frames. I'm concatenating two data frames here. I've sliced from the cancer data frame. I've sliced the target column only. So this is the slicing method. And after slicing it, I'm concatenating the data set in XS1, which means I'm concatenating it in the column based. So it. I'm concatenating both the several columns together. So let's see. Let's look at our new data frame now. So here you can see we have our new data frame where there are only two principal components. There are only two features, and with the two features we have the corresponding labels. So here I've what I did here is I've written some codes to visualize the data. So let's see how the data looks. So here you can see this red samples, this red dots, they show the malignant cells, and this green ones show the benign cells. So what you can do is, as I told you, using principal component analysis, it is easier to visualize data. So it is very important in unsupervised learning, because in unsupervised learning you can visualize the data, because you will be having a data of higher dimensions, not only two dimensions. But if you can reduce it to two dimensions or three dimensions, you can visualize the data and see if you can make your algorithm work, and if you can form clusters there. For example, you can form clusters here, because if you use KNN or any sort of clustering algorithm, you can form clusters here. But this data is separable in some way or the other, and but In other data, when it's in higher dimensions, it is more separable, but in two dimension it is separable as well. So it is good to visualize your data before running an unsupervised learning algorithm using PCA or single value decomposition methods. So after we are done with visualizing the data, we'll see what accuracy we have with the same algorithm I'll be using with the same random state. I'm using the random state of 40 because I'm saying I've already used the random state of 42 in the above cell. Now I'm using the random state of 42 in this cell as well, so that my data is distributed in the same manner. So after distributing it and running the same algorithm on the data, on this data, on the data where there are only two features. So we'll evaluate our model. Let's see what's the training accuracy and the testing accuracy. So here you can see the training accuracy and testing accuracy hasn't gone down by much. Previously we had a training accuracy of 95 and testing accuracy of 94. Here we have a training accuracy of 94 and testing accuracy of 93. So by losing 0.0, by losing 0.1 um, information percent of information, you have lost some accuracy. So but you could reduce the 29 or 30 dimensions. We have 30 dimensions here, so you could reduce the 30 dimensions to only two-dimensional data. You could make it a two-dimensional data. So this is where the PCA comes into play. This is why PCA is very important for you to learn. And you can look at another example. I've used another example here. So for from sklearn.dataset, you have another function which is called fetch openml. So this function can fetch any data set from the OpenML site. So you need to visit that site and see what that site has. It has a lot of data sets that you can play with. And this data set is a very popular data set. It's a very large data set where there are handwritten numbers that you can classify. So I'll be fetching this data. It will take some time to fetch the data from the OpenML site. So the dataset's name is, this is the dataset's name, and you can fetch it with this name, MNIST 784. I will quickly go through this. So here we can print out all the keys, and after printing out all the keys we can look at how much sample points we have. Here you can see we have 70,000 samples, 70,000 samples and 784 columns, and using all this thing will create a data frame. You can see the data frame contains only the pixel values, since I said this is a data set where there are images of handwritten numbers from 0 to 9. So and since I told you in PCA the first preliminary step is scaling the data, so you need to scale the data. So after scaling the data I will split the data, and after splitting the data, here you can see I'm using neural networks, and I'm using a multi-layer perceptron classifier, and I've used a three hidden layer. So the three hidden layer, the first layer contains 10 units, 10 hidden layer units. The second one contains 20 hidden units. The and the third one contains 7 hidden units. So let's see how much time it takes to train this data, since this is a large data set. So I need to import this data, this multi-layer perceptron classifier first. I did import it before, but since the runtime got restarted, I have to import it again. So I'll import the multi-layer perceptron classifier. After importing it, here you can see I've used another module from timeit. So timeit is a module which gives you a default timer, and you can extract it as a timer. So I've just changed the name. So, and what this does is it helps you calculate how much time your algorithm takes to train the data. Since this is a very large data set containing 70,000 sample points, so we'll see how much time it takes to train this data. So here you can see after training it for almost 2 minutes, we get a warning message that our model has not converged yet. So if we get this warning, what we need to do is we need to increase the maximum iterations. So maximum iterations by default we have 200. So I'll use 1000, which will take time. So let's train this and let's see how much time it takes. So you can see this didn't take much time either. It even took 2 minutes like the last time. So it took some seconds extra. So after doing it, we did not get the warning that our model did not converge. So let's see the performance of this model that we trained. So let's evaluate. So here we can see we have a good training and a testing accuracy. We have a training accuracy on a data set which is much large, which is which has 70,000 samples, and we have a testing accuracy of 93% using neural networks. That's why I keep on telling you, neural networks is very robust on large data sets. So as you feed it with more and more data, your neural networks will increase more and more because and with that you also need to increase the size of your neural network, because then the function that your neural network will generate will be much more complicated when you use a large data set with multiple number of rows and dimensions or columns. So what is the first step for for PCA? The first step of PCA is you have to scale the data, and after scaling the data we will fit the data, and after fitting the data we will create a new data frame with two PCA and the target values. You can see the target values where there are labels. If the number is 5, then it's 5. If the number is 0, then it's 0. So using the main df.target.unique, you can see all the values it contains. Here you can see it contains value from 0 to 9, and using this array and the this data frame, we can again generate a new plot. So let's see how our data looks. So here you can see in 2 dimensions the data looks very clumsy, the data looks not so separable, but in higher dimension the data is separable. That's why we got a very good accuracy. That's why we could fit it with 97% accuracy. We could separate the data accurately for 97%, and that's what I'm saying. So for this large data set, since you have reduced it to only 2 dimensions, so you have lost a lot of information. So since you lost a lot of information, let's see how much information you lost. So in order to do that, what we need to do is we need to do PCA dot explain variance ratio. Let's see how much information we lost. Here you can see we lost a lot of information. That's why our neural network will not do really well on this dataset, on this new dataset of only 2 dimensions. So here you can see we have lost a significant amount of information by reducing this 784 columns to only 2 columns. So we have lost a significant amount of information. So our neural network will not work really well on this two-dimensional data. From 784 dimensions, we have reduced it to two dimensions. So let's see what's the performance of this model, and we'll use the same number of iterations that we used above. So we'll use a maximum iteration of 1000, and let's see. So since we reduced the dimensions from 784 to only two dimensions, two features, the time taken is relatively very less, but you had to give up on your training and testing accuracy. Like the training and testing accuracy is very, very low. So what you can do is we'll reduce the 784 features into only 50 features. So let's create a PCA component of only n components of only 50, where we'll have 50 principal components. So let's see how. So after doing that, we need to create a new column where we'll have names like PCA1, PCA2, PCA3, and this is the list comprehension that I used. Um, So after that, we'll look at the explained variance to see how much information we lost. Here you can see we lost still significant amount of information. We lost 50% of information, and I'll pass the feature column as calls, and we'll look at the new data frame. So here you can see we have 50 principal component. We have reduced the dimensions from 784 to 50, and we cannot plot it into a graph, so we'll leave this code as it is. We won't touch that code cell, and from main.ref we will again use the train test split to split the data set, and after splitting it we'll train our model and see what's the testing accuracy and training accuracy we have. So here you can see after training it for 1 minute and 21 seconds, since we have significantly less dimensions, we did not take much time. We did not take much time, but we did take much more time than two dimensions, because there are more weights to assign, because we have 50 dimensions now, so we have to assign weights to almost 50 columns. So after doing that, you can see the performance of this model is not bad either. So we have reduced 784 columns to only 50 columns using PCA, and we are getting a testing accuracy of 94, which is actually good. So that's why I wanted to show you PCA is helpful on big data set your if the information lost is not much. So we have lost a lot of information here, but still we have a training and testing accuracy of 94 and 95, which is actually very good. And another thing what I want to show you is very simple, is like making pipelines in sklearn. So basically if you want to make a pipeline, so by pipeline what do I mean, you can import this class from sklearn.pipeline. You can import this class, and using this pipeline what you can do is um, you can create a pipeline using scalar, using the standard scalar that you will be using, and this is the name that I have given, and you have to pass it a list where you have a scalar and the classifier that you want, and using that you can do pipe.fit. When you do pipe.fit, the data is also scaled, plus your algorithms also runs on the training data. So but you need to split it. So here you can see I have split it 50,000 for the training, and for testing for the score I'm using the rest 20,000 data. So for for fitting I'm using the first 50,000 of the data, and I'm also passing the corresponding labels of those data first 50,000, and for the score I'm using this. So if I run this, you can see it will take some time. So here you can see we have trained our KNN model, and after training it we have an accuracy of, we're checking the accuracy on 20,000 data, that's why it's taking some time. You can reduce the testing size to even less. When you have a large data set, you do not need much of, you do not need relatively a big testing set when you have a large data set. Okay, and the last thing that I want to show you is that you can save and load your model. So from sklearn.externals, you can, what you can do is you can give a file name, and there's a library called joblib, and you do not have to use sklearn.externals as well, because in the newer version this joblib will not be there in the externals. So what you can do is you can give a file name, and then using job live.dump you can dump your model, and you can, when I do this, you will see that I'm getting a warning that job live will be removed, and it can be directly imported. You can do import job live, and then you can do job live.dump, and here you can see, if I show you the file, so here you can see I have this model. So now I can just download it. So the benefits behind this is you can save your model along with the weight and everything, because sometimes your model might take a long time to train. It can take 1 or 2 days, like depending on your data size and the model you're using. So it is a good thing to save your model. You do not have to train it over and over again. And using joblive.load, you can load your model into a variable, and after loading it, you can look at all the parameters I have used for my model, where I have used 10 hit 10 10 hidden units in the first hidden layer, and 20, then so on and so forth. And with my loaded model I can also see the score of my model, which was basically 94. And the last thing that I want to show you is I have tried to basically cover all the main domain of scikit-learn, but everything might seem little overwhelming now. So what I suggest you to go through all some of the algorithms that I showed you and try to understand them, and there are improvements on those algorithms. There are even better algorithms in the scikit-learn library that you can use depending on your problem. So this is the roadmap that you can follow. This is the scikit-learn cheat sheet that you can use. You'll find it in the scikit-learn library, and this flowchart gives you some intuition about the estimators and when you which estimators will be useful uh, tackling your data set. So if you have more than 50 if you have less than 50 samples, you get a thing called more data. Then you need to gather more data, and if you have more than 50 samples, then you can go to some predictions. Like if you have less than 100 samples, then you cannot use stochastic gradient regressor, and or so on and so forth. So this is the algorithm cheat sheet that you can use. So that's all from my side, and that's all from introduction to scikit-learn. And